Hi guys, this is Faizan and welcome to today's session on top 5 sorting algorithms by Great Learning. Now before I start, can you guys quickly confirm in the chat if I'm audible, is my screen visible, can you see the pointer that is there, right? If everything is okay, just quickly give me a confirmation in the chat, and in the meanwhile, let me give you a quick tour of how our academy looks like. Just go into the Google Chrome, type in Great Learning Academy, just click on the first link that is there, it will redirect you to this page. Herein, if you can see that these are the live sessions, if you want to view all the live sessions, just click on it and you will get all the live sessions. Okay, then come when you scroll down, you see the popular courses that are there, right? Digital marketing is there, graphic design, Python programming in Hindi, right? All these courses are available to you, right? And all these courses are free. If you are someone who is looking into data science, we have courses available on that as well. If you are someone who is interested in IT and software, we have courses available on IT and software, Python fundamentals, cybersecurity, ethical hacking, blockchains, CSS, HTML, all those things, right? And if someone is interested in Hindi, we have courses available in Hindi as well. You see, but we have Python programming in Hindi, machine learning is in Hindi, C, C++, React, R, AWS. All these courses are available to you guys, and these are all free courses. Once you have registered and you have gone through the content, and at the end you just have to answer 6 questions correctly out of 10 in order to get the completion certificate, right? So with that being said, let's continue with our session. So today we are going to talk about, okay, I can see some yeses, okay, great. So now today we are going to talk about top 5 sorting algorithms. So first we will talk about simplest sorting algorithm that is there, which is bubble sort. If you can see how bubble sort works, can anyone give me in the chat, can anyone tell me in a most naive way how bubble sort works? Just quickly write in the chat how it works. You don't have to be explicitly technical while you are explaining me. You just write in 2-3 words how it works. That's it. Harsh, we have Korea, we have Senthil. All of you, any one of you can answer in the chat. Yes, Bishal is there. Bishal, can you quickly just give me a 1 or 2 words, in 1 or 2 words, what is bubble sort, how it works? So we all know this is the easiest sorting algorithm, and it is a brute force. Brute force means straightforward, okay? Without thinking about efficiency, right? When you talk about algorithms, right? The one thing that will come up in your mind is efficiency, right? Is this algorithm efficient enough? Will this serve our purpose, right? So all these things will be there when you are talking about data structures and algorithms, right? The efficiency. Bubble sort is the simplest sorting algorithm that repeatedly steps through the list and compares adjacent elements and swaps them if they are in wrong order. Absolutely, Anirudh. Yes. So now you can either sort in descending order or in ascending order, right? Every element in bubble sort, how it works, every element, right? Every element is compared with the other element. We'll talk about demonstration as well as we will see the implementation, as well as we'll talk about the algorithm itself. Okay, so every element is compared with each other, right? So first element will be compared with second, then first element will be compared with third. Every time each element will be compared with all the rest of the elements, right? And at the end, this is very important, at the end we will have one such element at the end whose position will be fixed. Okay, this is most important thing. At the end we have that element that is there which we are comparing will have its original position, that is in the sorted array, will have its position fixed. Okay, we'll use nested loops for it. Okay, we'll talk about time and space complexity as well. Okay, so this is how it works, right? We have a for loop which runs from 0 to n, that is from first element to n element. Then we have another nested for loop which runs from 0 to n minus I minus 1. Why? Because at the end, why this I is there, when I will talk about the demonstration, I will explain you each and everything why this I is there. Minus 1 is since we are going to compare one ahead. You see if you observe carefully here, we are comparing j and j plus 1, so one ahead. So have we if we haven't written this minus 1, we will be comparing the last element with the element which is not there, right? Let's suppose if you have an array and the array is of 0, 1, 2, 3, 4 size, the size of the array is 4. At the end you have 6, let's suppose, and you're comparing it with j plus 1, right? This is what happens over here. So there is no element, right? You will get an error. Is this thing clear? Why I'm using this -1, and now why I'm using this I, it will be covered in the demonstration part. And then if that is the case, then if a of j is greater than a of j plus 1, then we will be swapping them. So if this is greater than this, we'll swap this. If this is greater than this, we'll swap them. If this is greater than this, we'll swap them. So at the end we will have the largest element that is there in the array. Simple, right? Is this thing clear? Quickly confirm in the chat. Is the algorithm part clear? Now why I have written this I, there's a logic behind it. I will explain it. Okay, apart from that, is everything clear? Quickly write in the chat, guys. So I will start with this as a very naive, very straightforward brute force algorithm, very easy algorithm. And if you have no idea about sorting algorithm, every time when a person is sorting anything, he will use this bubble sort. Okay, we'll talk about some complex algorithms as well, sorting algorithms, right? So now let's move on to the demonstration part. Okay, great. So now if you see, we have this iteration, this is the second iteration, right? So, okay. 1 minute. Yeah. So you have this input array, right? This is the array and you have these indexes in place, right? This is 1, 2, 3, 4, right? And this is these are the elements, okay? Sir, explain n minus, yes, Amruta. Yes, Amruta, I think I'm pronouncing it right. So yes, I will explain that n minus 1, I minus 1, I will explain it. First, I want you guys to be clear with this -1. Why I have written this -1. Is that thing clear to you, Amrita? Because we are comparing j and j plus 1. When we are at the end of the array, right? This is, let's suppose this is the end of the array. And we have 6 over here. The j pointer will be obviously here, right? Now, if we are comparing with j plus 1, then means we are comparing with this element which is not there. That means we are accessing memory which is not there. So that is why this -1 is there. Now why this I is there, I will explain it, okay? So now if you see, this is your input array, right? And let me just clear it. Now these are your elements, right? This is your input array and these are the elements. Now in the first iteration, what happens if you observe carefully, the outer loop 0 to n, the outer loop that is there will work from 0 to n. This thing is simple, right? And the inner loop will work from 0 to n minus 1. And there is -I also. I will talk about it also. Okay. So now this is the thing, right? And if a of j, that means this is j loop, this is your I. So you have your I over here and you have your j over here, right? This at this pointer, right? Now what we are doing, we are comparing these two elements, j and j plus 1, right? This is j and this will be j plus 1, right? Simple. If this is greater, if 10 is greater, then we will swap them. Else what we will do, we will just increment our j pointer. Now this time around j will be here, right? And I is fixed. Okay, we are just using that to iterate through all the elements so that each and every element is compared, and at the end we have the largest element. Okay, now what happens, now 16 will be compared with 11. Yes, it is smallest, right? So what happens, these will be swapped. Now what happens, again we'll be incrementing j and j will be here. 16 and 20 will be compared, and since 16 is less than 20, nothing will happen and j will move ahead. Then 20 and 23 will be compared and nothing will happen, and we are done with our first iteration of the inner loop, right? And the outer loop is working from 0 to n, right? So in the first iteration where I is 0, if you see, in the first iteration where I is 0, we are done with this and we will have some kind of this structure, right? 16, 20 and 23, right? What happens after that? What happens after that? Now, once we are done with this thing, once we are done with the entire first iteration, you see 23 is the largest element in this entire array, right? Is this thing clear, guys? Once we are done with the entire iteration, right, from 0 to n in the inner loop, right, the 23 have its original position, that will be there when you sort this array. This will be its original position, right? Is this thing clear? Quickly write a yes or no. Just quickly write a yes. Is this thing clear? Is the first iteration clear? How it happens? Since this is simple, very simple algorithm. We are just checking. The outer loop is to iterate through all the elements. The inner loop is just to check j and j plus 1. If that is smaller, then we will swap. If that is greater, j is greater than j plus 1, we will swap them, else we will keep it as it is. So in this case it is as it is. In this case this was greater than, okay, Animesh says no, okay, Bishwa says yes. So if this is greater than this, we will swap them. If this is greater than, we will not swap them because 16 is less than this. 20 is not greater than, we will not swap this, right? Now this 23 is at its original position in the sorted array as well. Now what I am doing in the inner loop, if you observe, I used this term, right? N minus I minus 1. So minus 1 is clear, right? Now why minus I? If you see, now it's pointless to compare this 23 because it is at its original position. We do not want to compare the element that is already greater than the entire array, right? This is the element that is greater than all the elements. So why we are comparing it? So this is what happens over here. Now next time around, the value of I will be 1. So this time around, we'll be skipping this element. Is this thing clear? Now you understood why I have written this n minus I minus 1. Ahmed, Krishna, Das, Amurtha, Kharat, Harsh, Vishal. Is this thing clear, guys? Shakir, is this thing clear, guys? Is this thing clear? Why I have written this n minus I minus 1? Because now in the next iteration, let me just go through the next iteration as well. Obviously, you can write it. Yes, Kharat, you can write it. It doesn't matter. N minus 1 minus I. It doesn't matter, right? So, can you give you... Okay. So, Rohit, in that case, you can just post it in the chat, in the comment section. We'll answer it. We'll definitely answer it. Okay? You don't have to just get the email IDs of someone. You just write it, then it opens the a domain for each and every one of us, right? Even if someone is learning, he will also understand what is the problem that you are facing, and he will think about it. Even if someone not from grade learning can answer it as well, right? So just write it in the comment section. Okay, great. So now what happens in the next iteration? If you observe carefully, now earlier I was at this position, now I is at this position, right? Now j is still we are iterating our j pointer again from 0, right? So this is our j pointer and this is our j plus 1. So again these two will be compared. Now you might be thinking, okay sir, why we are comparing it again and again? If something, that is the drawback of bubble sort. It is one of the most straightforward algorithm, that is brute force algorithm, without thinking about time efficiency, that is time, right? Time efficiency, we don't care about time efficiency in this algorithm. This is the most straightforward algorithm, that's it. Okay, now what happens? We are comparing it again. Since 10 is less than 11, nothing will happen. 11 will be compared with 16, nothing will happen. 16 will be compared with 20, nothing will happen. And then we will stop. Why? Because we have already this thing in place, n minus I minus 1. So this time around, n, let's suppose, what is the value of n? It will be 1, 2, 3, 4, 5. 5 minus I will be 1 and minus I. So 3. So we'll iterate only 3 times from 0 to 3. That is 4 times. So first, second, and then third. Okay, that's it. Done. And then what happens? We are done, right? Okay. So now, next time around, this thing is stopped. Now, if you observe carefully, again, this 20 is the largest element in the entire array, right? Now, after the second iteration is done, the third iteration will be there, right? So, second iteration, 0 iteration is done, first is done, second is done, third is done, fourth is done. So, if you observe carefully, the outer loop is working n times, right? That is the number of elements in the array, right? Does that make sense? 0, 1, 2, 3, 4. The five elements are there. The outer loop will work 5 times. So, that is why we have these iterations from what? 0, 1, and then you have 2, then you have 3, then you have 4. Okay, so every time the last element will be fixed, and next time around we will be skipping that. Is this thing clear? Now this is how bubble sort works. Okay, done with the demonstration. Let's see its implementation. Okay, so now what you will do, you will have your array and you will calculate the input size, that is the length of the array, and then you will iterate this outer loop from 0 to n, that is the size of the array. So obviously 0 to n, that means the n will not be compared, that means you will iterate 5 times. Okay, so if 5 is the size of the array, you will go from 0 to 4 including 4. Okay, so now this time around you will be iterating from what? 0 to less than, so j should be less than size, that is 5 will be the size of the array, minus I, this time around, first time around I will be 0, and minus 1. So the outer loop will work n minus 1 times. Now this will happen in such a way that outer loop will work first time around, it will work for n minus 1, next time n minus 2, next n minus 3. So overall the inner loop will work how many times? N times. The outer loop will work n times. Now that will be something that is familiar to you guys. When outer loop is working n times, inner loop is working n times, that means the time complexity will be simple n square. Okay, so now we'll get back, after this slide is over, we'll get back to time complexity as well. Now this thing is clear, right? Here we are doing nothing, but we are just swapping the elements. So if a or j is greater than j plus 1, we'll swap them, else we keep it as it is. Okay, okay, done. So this is your bubble sort. Okay, done. Now let's see what is the time complexity. So if you talk about time complexity, in the worst case, when your array is not sorted and every element is haphazardly placed, at that time around each and everything happens, right? Outer loop will work n times, right? So for one element it will go from, so the inner loop will work n minus 1 times first, then n minus 2, then n minus 3, and so on to 1. Okay, so we have n square complexity. So average case is also n complexity, big O of n square, the time complexity. But what happens in the best case? Now the best case is very important, guys. So let's suppose, let me take a simple example. Let's suppose your array is sorted, right? Let's suppose we have 5, 6, 7, 8, 9. This is our array. Okay, 0, 1, 2, 3, 4, right? This is our array and it is sorted. Now since if we do not modify our bubble sort, right, we are not doing any modification right now, if that will be the case, then again it will be n square. If we are not modifying our bubble sort, that is very important, right? And it has been asked multiple times by multiple companies, right? How you can, if you do a simple modification in your bubble sort, the best time complexity will reduce from from n square to n, that is linear. How? You just need to implement one simple thing. Just enter a flag in here. Okay, let me just show you in the implementation. Let me just clear it. So if you just insert a flag in here, let's suppose you have int flag and flag is equal to 0 or 1, anything, right? Then you will do what? If flag is 0, right, and if it has entered this loop, right, AR of j is greater than AR of j plus 1, right? If it has entered this loop, just update your flag to 1. Okay, and then check at the end if flag is equal to 1. If it has entered this loop, that means your array is not sorted. Okay, there was some case where AR of j is greater than, which will not be the case if your array is sorted. Let's suppose, let me take an example, 6, 7, 8, 9. If, will this case hold? Will this if block be executed in this case? Is AR of j greater than AR of j plus 1? No. Is this greater than this? No. Is this greater than this? No. It will never enter this thing, right? So flag will be still 0. Now if you check, if flag is equal to 1, then you continue. Else if flag is 0, then what you will do? You will break out of this loop, the outer loop. That means this array was already sorted and you only iterated single time. That is when you're talking about this for loop. Okay, the outer loop will be executed only once and this loop will be executed n minus 1 times, which boils down to big O of n. Is this thing clear? Just a small modification that you used flag variable and then you implemented, or it's also known as modified bubble sort. Okay, so if you have modified it a little bit, your time complexity in best case will boil down to big O of n, that is linear time. Okay, done. Now what about the space complexity? Since you are not using any auxiliary memory can be in the form of stack, it can be in the form of queue, it can be in the form of linked list or an array or a string that is of n size. Okay, the number of elements. So since you are not using any of these auxiliary memories, so your time, your space complexity will be constant. Okay, we'll also talk about some cases where you are not using your any extra memory, but still your space complexity will be big O of n. We'll talk about those cases as well in this session. Okay, done. Is this bubble sort clear, guys? Quickly write in the chat so that we can move on to the next sorting algorithm. Okay, quickly. Is the modified bubble sort clear to you guys? Quickly, guys. I want answers from you guys. Guys, this is very important, right? This is very important for you to write in the chat so that I can understand that you guys are understanding. Okay, quickly. Okay, great, great. So now let's talk about another algorithm, which is selection sort algorithm. Now, if you have observed, if you have just gone through these algorithms, right, the bubble sort, you might be thinking, okay, sir, done. We are comparing each and every element every time, and we are just swapping them. Is there a better way wherein we can just select something and then compare it with all, and we can just reduce our this what number of swaps? Yes, this is the algorithm, the selection sort algorithm, which helps us to reduce our swaps. Okay, so it is the simple sort algorithm, right? This is simple. Then bubble sort, right? And it revolves around comparisons. Okay, so number of comparisons will be same, but sir, can you explain how to calculate the time complexity? So basically what we are doing over here, so in you have something that is known as what the time complexity boils down to two cases, right? M plus n and m into n. When you have a nested for loop, right, I will give you just a gist of it. Okay, the when you have a for loop, and inside that for loop you have another for loop, and both these for loops are running from 0 to n. In this case, this will be the case of m into n, right? The both of these are nested. That means you will multiply the time complexity of this with this, so that is why in these cases you will get your time complexity as n square. Now this won't be always, right? It doesn't depend, it doesn't mean that every time when you have a for loop that is running from 0 to n, and inside the for loop that is running from 0 to let's suppose every time you are dividing your sub problem inside that for loop. Okay, let me just clear it out. So let's suppose you have a for loop that is running from 0 to n, and inside that for loop you are running this for loop what every time you are dividing this for loop by n by 2, right? You're dividing your search space. Now this doesn't mean that this is also n square case, right? This means that this is the case where let's suppose this is running from 0 to 8. That means this is running from 8, this is running 8 times, and inside that it is running only 3 times. That means this will be the case of this, right? What is the value of this thing? Log 8 to the base 2, it will be 3, right? So if inner loop is working 3 times, outer loop is working 8 times, that means this is the case of n into log n. Now this will be the time complexity in this case, right? Don't just mug it up that every time you have a nested for loop, then that will be the case of n square time complexity. No, it depends upon the outer loop, how many times it is working, the inner loop, how many times it is working. Now if we have seen the earlier case where we modified our bubble sort, in that case our time complexity was big O of n, even though we have a nested for loop, right? But the conditions that we applied on this for loop makes this we are only running this outer for loop single time, right? Because our array is sorted, so this takes a constant amount of time, right? It's running only single unit of time, right? And the inner loop is working from 0 to n times, so that is why the time complexity of these two nested for loops is order of n, big O of n, right? And we always talk about worst case, right? We never talk about best cases. When you're talking about time complexity, you always take into consideration the worst case. Okay, that thing should be clear. Okay, so now let's move on to the selection sort. Now every time you have, in each iteration, your one element gets placed, right? And that will be basically what we are doing. We'll choose the we'll pick one element and compare it with all the elements. Now that element which we picked will be the minimum element in the entire array, and then what we will be doing, we'll just swap that element with the first position, right? In the first case, we will always and we'll swap it with the first element, and that first element will be fixed. Now we know that this is it specially for one programming language, or it will work for all of them? No, it is this time complexity are you talking about, Amit? It will work for all the programming languages. It's not that language specific time complexity. Okay, it will work for all of them. Okay, so we can choose the maximum element. We can also choose either we can go for the maximum element and replace it at the end, or we can go with the minimum element and replace it at the with the starting index. Okay, selection sort basically selects an element, and in every iteration it places it in the appropriate position. Okay, if I'm looking on this side, guys, don't get confused. I'm looking at your chat, guys, so that is why I want you guys to be continuously writing in the chat if anything is clear, everything is clear. If you are not getting anything, just tell me. Okay, so this is whole what a selection sort is. Now let's see the algorithm and then maybe we will understand it better. Okay, so now this is the algorithm. Here, if you observe carefully, we will iterate, the outer loop will iterate from n minus 1 times. That means the first element is sorted in itself. Okay, now the first element that is unsorted will be the minimum index, right? So let's suppose we are now, this time around, we are calculating the minimum element. Now what we will do, we'll calculate, now this is the index of that minimum element. Okay, so this will be 0 at starting. Okay, now every time we'll compare this 0th element with all the elements that are in the array. Now if that is the case, now if this is the minimum element, that is what is going on. Jamie, we are trying to understand a selection sort algorithm. Okay, if you're not if you have just joined, maybe just give yourself a little bit of time. Okay, and maybe you will get things. Okay, so now what happens, now we have this element and we are comparing it with the current minimum that we have, that is the 0th index element. Okay, so now if that is the case, then we will swap them at the end. Okay, now with each iteration our element will be fixed. Let's look at the demonstration, then things will be much clearer. Okay, so now what happens, we have this element, right, the 0th index, right? We start iterating from it. Okay, let me just go through this first. And okay, so now let's talk about first implementation, then we will move to demonstration, because then things will be clear for you guys. Okay, so now what happens over here, we have this size and we calculate the size. Now this outer loop is working from 0 to size minus 1. Okay, that means we are iterating from n minus 1 positions. Okay, done. Then we have this j as minimum, that is the first element is the minimum index. This minimum is nothing but the index of the minimum element. Okay, index of the minimum element. Then in the inner loop, what is happening, we are comparing with this, we are comparing this j, we are comparing this I with j plus 1. Same thing which happened in bubble sort. Okay, just give it some think about it in a broader way. Okay, don't just be stuck with bubble sort. Think now what we are doing, we are comparing we have this j and we are comparing this j with I plus 1, or we are comparing this j with I plus 1 this time around, right? So we have the 0 in place, right? We have this array, right? And we have j over here and we have I, which is pointing to j plus 1. Okay, so now what happens, now we are comparing this I, right? This I, we are comparing it with the minimum, that is nothing but this element, right? If it is the minimum index, right, this is the element which is minimum than this. Okay, let's suppose this is 5 and this is 6. Now in this case, this is not the minimum, right? Nothing will happen, we'll move along. Okay, now I will be here. This time around, this is 3. Obviously this is less than. Now this will be our new minimum. Okay, this will be the this will be our new minimum, and we will be storing not the element but the index. Okay, so what will be the index of this? This will be 2. Done. Now next time around, what happens, we'll iterate again. So this time around I will be here, and let's suppose this is 4. Nothing will happen. Now this is 2. Okay, now this time around, this is minimum than 3, right? Obviously this ARR of I is minimum than this 3. So now this will be our new minimum. What is the index of this? This will be 4. Now we update our minimum. Now if you observe carefully, every time we have a minimum, we are just updating our min. Now let's go back to this. Okay, this demonstration. Now this is our minimum index, okay, which is 0. Our I is pointing to this, or j is pointing to this, and I is here. Okay, now we are comparing what? We are comparing these two elements. Okay, 23 and 10. We saw, okay, 10 is minimum than 23. Yes, it is. We didn't swap these elements, which was in the case of bubble sort. We were swapping, continuously swapping. We have now reduced the number of swaps. Okay, now this minimum will be updated. Now this minimum is 1. Again, we increment our I. Now we will be comparing this I with the new minimum, which is 10. These two will be compared. Okay, nothing will happen. I will be incremented. 11 and 10 will be compared. Nothing will happen. Okay, 20 and 10, nothing will happen. Now what has happened over here, right? our minimum index is at this position. That means minimum after one iteration is 1. Okay, so this is the first step. Okay, now what happens after that? Let me go back to the algorithm. Now once we have calculated this bin, after that swapping will happen. The last swap will happen with the first element. Okay, that is the temporary ARR of j, which is pointing to 0. So that is what is happening in this position. So now we have this 1, that is 10, and it will be swapped with this 0, that is the first element, right? So rest of the elements, if you observe carefully, rest of the elements remain as it is. Okay, so all these elements 10 and 23, these were swapped. That means only one swapping happened, which was not in the case of bubble sort. Every time we have a minimum, we were swapping them in bubble sort, but this time around we selected the minimum index and then swapped it with the first element, right? And now what happened? This 23 is swapped with this, and rest of all the elements, that is 16, 11 and 20, will remain as its own position because we didn't swap them. Okay, done. So now if you observe carefully, this is our new sorted part. Is there any element that is less than 10? No, this is our new sorted part. Now next time around what will happen, if you observe carefully over this, so in the next iteration what will happen? Now j will be incremented. Okay, so j will be incremented. Now let's go back to the demonstration. Now next time around, let me just erase this. So next time around, this is our new j, this will be I. Okay, this will be I over here. Now again these will be compared. What? And minimum will point to this element, ARR of j, that is minimum is at index 1. Okay, so now what happened? We compared this 23 with 10. Is this the minimum? Yes, min got updated to 2, index 2. Next time around, is 16 less than? Yes, min got updated to 3. Is 11 less than 20? No, so minimum is at index 3. Now what will happen? You guessed it right, these two elements will be swapped. Okay, done. So now we have 11 over here and 23 over here. Rest of the elements will be as it is. Is this thing clear, guys? Is this sorting algorithm clear? Is the demonstration part clear? And next, in the next iteration, what will happen? We'll fix these portions, right? So this time around, we will have minimum element at this position. Next time around, minimum element at this position. And finally, we have this sorted array. Okay, this is selection. We will pick one index, that is the first index. Obviously, I told you at the earlier, we are picking the minimum. You also can pick the largest. Okay. No, Akash, yes, merge sort is not the best in all the cases. Okay, it is not that merge sort will always suffice your needs according to the application. It depends, right? So let's suppose I'm saying that you have a system where you cannot use any extra memory. Okay, now you are stuck, right? Sir, repeat once more. Which part is not clear, guys? Quickly. So in the meantime, Akash, it cannot suffice your need in that case when I told you, okay, you cannot use any extra memory. And I'm giving you one more condition, that your array is almost sorted, and then you need to just sort the some part of it. In that case, if you use maybe quick sort, then at that time around your time complexity will reduce from even n log n to n log k, the number of positions that are sorted. Let's suppose you have an array and therein you have half of your array, or k elements are sorted, or let me take an example in such a way that you have an array which is k sorted array or nearly sorted array. In that case, you cannot use merge sort. Okay, do it a little bit slower. Okay, crystal clear. Okay, some of you saying crystal clear, a bit slow. Okay, no problem. I will do you want me to repeat, guys, or is this thing clear? So let me just go through or walk through again through this sorting algorithm, through the selection sort again. Okay, so with the implementation part. Okay, this step is clear. We are just calling the function, we have the size, and then we are iterating from what, 0 to size minus 1. Okay, so now I told you I'm picking up the minimum element. You can also pick the maximum. At that time around, you will go at the end of the array. Okay, now in this case, I'm picking minimum, and that is j, that is the first element. Okay, let's suppose this is your array, 5 4 then you have 10, then you have 2, then you have 20, not 20, let me take 9. Okay, so now you have these indexes in place. What happens over here? Now j is pointing to this, right? j is pointing to this, and this is the minimum index. We supposed it because we are picking the minimum element in the entire array. Now this is our minimum. Okay, now our I starts from j plus 1, that is I is pointing to this. Now what we are doing, we will compare. It is a comparison algorithm, guys. So we'll be comparing more and focusing less on swapping. We'll swap only once at the end. Okay, so if you can observe here, if you can just go with the intuition, you can obviously compare. If you compare it with the bubble sort, you can clearly understand that number of swapping is less than the number of swapping in selection sort. Okay, done. So now what we are doing, we are comparing AR of I with the minimum. So we compared them. Okay, so we compared them. Okay, we thought that, okay, so now this 4 is less than 5, so this will be our new minimum. So minimum was pointing to 0, now it's pointing to 1 index wise. Okay, so now I will be incremented. I is pointing to this 10. Again we compared this 10 with the minimum index, that is 4. No, it is not greater than this. We updated our I, we incremented our I is pointing to this. Now I, ARR of I, that is 2, will be compared with ARR of min. Min is nothing but at index 1, that is ARR of 1, which is 4. So 2 and 4 will be compared. Okay, now we understand, okay, this 2 is less than 4, so we updated our min. Okay, so next time around 9, I got updated and we compared it with the minimum, that is 2. We didn't do anything. Now nothing is swapped. In the first entire iteration, no element is swapped. Now this entire loop is over, right? Now after that we will swap this in this. This is the swapping that happens. Now we swap this with the j, right? If you see this, the j, and j is nothing but this. So now this 5 will be swapped with 2. So after one iteration, only one swapping will happen, which will be 2, 4, 10, and then 5 will be here, and 9. So if you observe carefully, only single swap happened, that is with the minimum index, that is the minimum index which was 3, and the first element. Because now we are fixing that this element is the sorted part, is your sorted part, and it will not change its position in the entire sorted array. So obviously 2 is the minimum element in the entire array. Similarly, you can go for the largest element as well. Okay, done. Now let's move ahead with the time complexity. Now if you talk about time complexity, obviously there are two for loops, right, and nested for loops, and there is nothing with by which we can just modify selection sort, and you can reduce the time complexity. So in each and every case, in the worst case that we already seen, it will be big O of n square, and in the average case it will be big O of n square. So basically in average case some of the elements will be sorted, but it will be n square by 2. So again we'll get the removing the constants and all those things, negotiating the constants, will still get n square. But in the best case you might be thinking, okay sir, now what if this is we have an array and which is already sorted, but do you have a mechanism wherein you can just stop it and do not compare it? No, you don't have, right? If you have 5, 6, 7, 8, and 9, you have a sorted array, right? It is the best case, right? So your j will be here, and still you will be comparing with this thing. You will be going through all the elements in, you will be comparing them, okay, with this. Then I with the minimum, then 8 with the minimum, then 9 with the minimum, right? So entire iteration is done. So 5 will be swapped with itself, right? So again, in the next time around, it will be compared, and then at the end 6 will be swapped with itself. 7 will be swapped with itself, 8 will be swapped with itself, 9 will be swapped with itself. Now in the best case also, since you are iterating through all the elements and inside that you are checking through all the elements, still it is big O of n square. Okay, so we have a question. If question doesn't tell us use specific algorithm, which is the best algorithm to use, bubble sort, merge sort, or selection sort? So Sandesh, it depends, right? If the question doesn't ask, you should, if you're implementing it through Java, why you are going to go through the pain of implementing any sorting algorithm? Just use arrays.sort. That's it, done. Merge sort applied. Okay, now if something you are implementing, or you're trying to code something which is not in Java and you have to explicitly code in it, why not go for something that is bubble sort? This is simplest, just go swap all the elements. But now if the interviewer is specifically asking for you to do a trade-off between either the space or the time, now if he's doing a trade-off between space, then you should definitely go for merge sort. Now if he has explicitly told you, now I can manage with time, but space is very important for me, so at that time you should go for quick sort. And if there is some explicitly any example which solves, let's suppose bubble sort works in wait, let me get insertion sort works in that scenario, and it works efficiently in that scenario when you have stream of numbers and those numbers kept on increasing. Okay. Okay, yes, we will go to that as well, Kadam. Okay, sir, loop within a loop known as nested loop. Yes. Loop within a loop, nested loop. Okay, so this is done. N square, yes. Okay, great. Every sorting technique is specifically important in case it's required. Yes, definitely. Okay, sir, merge sort. Yes, we will try to cover that as well. Okay, so now what about the space complexity? Simple, constant. Why? Because we are not using any of these auxiliary memories, arrays, linked list, stacks, queues, and all those things. Okay, done. Okay. Yes, Rohit, I will come to quick sort as well. Okay, don't worry. So now insertion sort. Okay, so I will go through insertion sort quickly. If you have any doubts, please post them. Okay, then we can move to quick and merge as well. Okay, so now insertion sort. So in insertion sort, think of an example wherein you are playing cards. Okay, now if you're playing cards, let's suppose you have this single card in hand. Okay, and rest of all the cards are on the deck, right? And obviously when you're talking about this card that is in your hand, is there any way you can sort it? No, this is something that is in your hand and it is already sorted. Okay, Anivesha says space complexity constant. Yes, space complexity is constant. Do you have any doubt regarding that? If yes, please write down in the chat section. Okay, so now may we get this PPT? Yes, it will be shared with you guys. Okay, don't worry. So now what happens? So now you have this card in place in your hand, and now you're checking this card that is in your hand and you're comparing it with the card with which you just picked. Okay, now one by one you will be picking them. Okay, now you will be comparing them. Okay, so this is your sorted part. Insertion sort will work in such a manner that this is your sorted part, and this will be, that is all the elements that are on the deck or the cards that are on your deck will be unsorted. Okay, this is unsorted and this is sorted, right? So insertion sort works in such manner. So you can this is also again a brute force algorithm, straightforward algorithm, there is nothing to it. Okay, so now it is just like playing cards. Now you have your sorted part and you have your unsorted part. Now first element, if you talk about one single element, do you require to sort this thing? No, this is a single element and this is sorted in itself, you don't have to sort it. Now you will be comparing it with the element that is here, and now you will be sorting them, right? So you have this element and you have this element, you will be comparing them. Okay, this is smaller, then you will swap them. Okay, now again next time around, in the next iteration, you have two elements in your hand and both of them are sorted. Okay, so now you have two elements in your hand, both of them are sorted. Now next element comes, you compare it with this element. Okay, if this is not greater than this, if this element is not greater than the element, let me just write it, then things will be clear. So this is sorted, right? You have 0, let's suppose you have 6 and 8. Now you have over here you have 9. Okay, sir, please attach the PPT in the description after ending the session. Sure, Akash, sure. So now what happens, you have this 9, right? Obviously now this 9 is greater than this. Now you won't be doing anything to the rest of the elements, right? So now again you will be have something there that is 6, 8, 9, which is sorted in itself, and you have this part. Okay, you might not be able to see this. Okay, so now what happens over here, you have this 6, 9, 8 and 9 which is sorted in itself, and then you will be picking up one more element which is there. Okay, done. So now let's see, this case happens unless and until all the elements are exhausted. Okay, done. So this is how insertion sort works. Okay, so now let's quickly go ahead and see the algorithm. Okay, so now you might be thinking, okay, so let me just skip this algorithm and let's go straight away go into the implementation. Okay, now if you observe carefully, why I am starting this iteration from the first element, can anyone tell me? Because I have already told you the single element that is in your hand is already sorted, right? So that is why I'm starting my iteration from the first element. Okay, and to the end. Okay, up to the end, done. And after that, what I'm doing now, since we have this element, right, that is 1, or let me take it an example as 8. Okay, so now this is your 0th index and this is your, let me just clear it out and then things will be clearer. Okay, so now you have this 0th index and this is 8. Okay, and you have rest of the elements 1 2 3 4 5, and let's suppose this is 7, then you have 10, then you have 6, then you have 4, and then finally you have 5. Okay, done. These are your elements. Now this is your sorted part and this is your unsorted part. Okay, and now what you will be doing, you will be storing this element. Now this is very tricky, this part is very tricky, try to understand it. Okay, now what you will be doing, you will start your iteration from here. So I is here. Okay, so that is why I'm starting from 1, because first element is sorted in itself, you don't need to sort it. Now what I'm doing, I am storing this value, okay, in temp. Why I'm storing it, I will tell you. Okay, so I'm storing it in temp. Then after that what happens, I'm using another pointer, that is j, which is pointing to this index, that is I minus 1, which is this, because now we have this element that is in my hand and we have something that is on the deck. Now I will be going backwards, right, I will be going backwards to check if this is less than this, right, only then we can find out the sorting part, right. So now we check. Okay, now we check. Now this condition, again I will let you know in a bit, in a while, right, so don't worry about this condition. Now what I am doing, I am checking if this temp, that is this 7, if this 7 is less than 8. Yes, it is less than ARR of j. So now what happens, I am decrementing my, what happens, first I will be changing these two values, right, this step is very important. Now what I will be doing, I'll be changing these two. So this 8 will remain here. Okay, now I'll be doing 8 over here. Now if you observe carefully, now you might be thinking, okay sir, we lost our 7, right, and for the same reason, so that our 7th element, that is the 7th the element that is there 7 will not be lost, I am using this temporary variable to store that. Done. But now we have an array which is 8 and 8, right, so this is also 8. Now what happens, now again, so obviously j was greater than here, because j was greater than 0 or equal to 0. This time around it was equal to 0. Now again I'll be checking for the rest of the elements as well, so I'm decrementing j. Now this time around j will be minus 1. Will this condition hold? No, because there are no elements on the left hand side, so this condition will not hold and we are out of the while loop. And then finally what happens, now what we'll be doing, we'll be doing ARR of j plus 1, that is j is at minus 1, so minus 1 plus 1 is 0. So now ARR of 0 will be replaced with temp, which is this element, which is temp, and which is nothing but your 7. Done. This whole thing happens in a single iteration. Let's move to the demonstration. Okay, so now if you see what happens, we'll be comparing this, right, we will have 23 and we have 10. Now we'll be comparing them and nothing, this is the first step, this is your first step, right, making the sorted part. This is the sorted element and this is the unsorted part. Now in the first iteration nothing will happen to the rest of the elements, right, they will be as it is, only these two elements will be swapped. Done. 10 is here, 23 is here. This is after first iteration, that is I equal to 1. Done. Now what happens in the second iteration, we'll be picking this 16, right, and we'll be checking, is this less than 23? Yes, it is. Now what will be happening, this will be also stored in temp, right, can we get a certificate for this? No. Okay, so temp, we're storing this 16 in temp, right, and what happens, this 16, we swap this 23 with this 16, so we have 23 and 16 is stored, right. Now again this 16 will be compared with this 10, right, and it will be stored with, it will be replaced with this index. So we have here, now at the end of this, then we have the final swapping, right, so we have 10 and 23, and at the end we'll be having this 16. Okay, no 16, in this case 16 is not less than, right, so let me just erase it. So what happens over here, now 16 will be compared with this 10, so 10 is, since 10 is less than, so nothing will happen. Now what happens at the end will be, this is not less than 16, so what happens, this 23 will be replaced with this 16. So that is what happened over here. So we have 10, 16 and 23. This is your sorted part and this is your unsorted part. Done. So let's move to the third iteration. So third iteration, you will be picking up one more element, that is this element. Is this thing clear, guys? This is simple, right? So you will be straight away going through all the elements and then picking up one element, comparing it, adding it to the sorted part, then picking up one more element, checking it with the sorted part, placing it at its original position, picking up one more element, again you have a sorted part, you have an unsorted part, again picking up one more element and comparing it. So the only thing that is there to understand in this algorithm is storing this variable over here. This is very important, you need to store it. And second, you should not go beyond the limit of the array, that is 0th index. You should not go beyond 0, okay, because there is no such element. Okay, quickly confirm, is this thing clear, so that we can move on to the quick sort algorithm. Quickly write in the chat, guys, quickly, if this thing is clear. If you want me to repeat, so that we can always have a next session, right? You don't have to worry, we can always go back and revise this thing. Okay, this session will be there on the YouTube. You can always reiterate through if you have missed something. Okay, so cool, so I can see some yeses. Okay, great. So now let's move on to the time complexity. Now obviously, if you have a sorted array, then you will not iterate backwards, right? So it is quite obvious, right? Now if you have a sorted array 5, 6, 7, 8 and 9, right? So now you have this, I will be here, right, and I will be here, and this is your first element. Now it will be compared, nothing will happen. So you will not go into that while loop, in that this while loop, inner while loop. Always you will not go in this while loop. Why? Because this condition will never hold. This will be always false when your array is sorted. Think about it. Okay, okay, so if your array is sorted, your temp will never be less than ARR of j, because your array is already sorted. Okay, so now in that case, that will be your best case scenario, and in that case your time complexity will be linear, because you are not going through this while loop ever. So obviously the outer loop is working n-1 times, which can always boil down to what? N. So big of n is the time complexity. Done. So in worst case, it will go through all the elements, that is n square, and same goes for the average case as well, average case time complexity. Done. And now if you talk about space complexity, similar to what we have seen earlier in bubble and selection. So insertion also takes constant amount of time, because we are not using any of the arrays, linked lists, stacks, queues, anything. Okay, no auxiliary memory is used. Done. Now let's quickly move, and is everything clear? Quickly guys, just quickly give me a confirmation in the chat if each of these three algorithms is clear to you. Are you able to understand each and everything, so that we can move on to this quick sort algorithm quickly? Guys, I'm waiting for your response. Okay, great. So now let's see quick sort algorithm. Now it is the most widely used algorithm when you are thinking about, when you are trying to use your memory efficiently. Okay, this is the go-to guy. Okay, it follows a paradigm of divide and conquer, which is very important. Okay, so divide and conquer is nothing but you will be dividing your problem. Okay, you have a problem and you will be dividing it into sub problems, and then further you will be dividing it into sub problems. So when you are doing those sub problems thing, right, you are dividing your problem into sub problems, and then when you're combining it, or when you're conquering through it, because once you're dividing it and then you have a particular scenario wherein you will have that element at its original position in this case, right? Okay, can you please take us the session on time and space complexity? Sure, Raghav, sure, that can be arranged. Okay, okay, great. So now what happens, it follows a paradigm of divide and conquer. Every time you search space or whatever is the array, and you will be dividing it into further sub problems, then those problems will be conquered, and in this case you will understand how divide and conquer will hold in quicksort. Okay, so we'll be using recursion, and you will have something that is known as pivot element in quicksort, which is nothing but the element, and you can choose any element as pivot. Now in this case I will be picking up the last element. Okay, so I have implementation on the last element as well. So I'll pick up one element which is my pivot element, which is nothing but that element after when I'm dividing it into further sub problems, that element after the entire iteration is done, or the recursive calls is done, that element will have its original position in the entire array as well. That means when you sort the entire array, that element will have its original position fixed after the all the recursive calls are done. Okay, so can you tell us about linked list? PM, not possible in this session, maybe in data structure. I already taken a session, took a session on data structures and algorithms. You can check. You once subscribe to our channel, you will get all the sessions that I have taken on data structures and algorithms will be there. Okay, just go through them once. Okay, it is nothing that therein I have explained each and everything. Okay, all the implementation. Okay, now we have chosen a pivot element, and it will be arranged in such a way that if you have your pivot element, all the elements on the left hand side and all the elements on the right hand side will be these will be all the elements that are less than pivot, and these will be all the elements that are greater than pivot. Okay, we'll arrange it, we'll see how it works. Okay, and after every call, the pivot occupies its original position. That means after the first call, this pivot will be there, and next time around this will be the pivot and this will be the pivot. So last elements will be the pivot. So again, sub problems will be divided. Let me take an example over here. Okay, so pivot can be any element. Okay, so in this, and its time complexity will depend on which element you are picking as your pivot. We'll talk about that as well in time complexity. Okay, so let me just go on to the next slide. Okay, so now if you observe carefully, now why this condition is there, we'll talk about it. Okay, so now every time, let's suppose you have this array 5 4 6 and 10. Okay, is this sorted? No. So now what happens, I am picking up this element as pivot. Okay, so now once this pivot is there, now what happens in the entire array, when an entire array is sorted, after first recursive call, this 10 will have its original position, and all the elements that are on the left hand side will be less than this 10, and in this case we will not have any elements on the right hand side which will be obviously greater than this 10. Okay, so now we are implementing this quick sort in a recursive manner, right? We are using recursion. So now what we will do, let's go through this partition. Okay, first how you will partition. Okay, how you will pick up this. Sir, can you take any number as pivot element? Yes, you can take any number as pivot, but I will tell you how your time complexity depend on what pivot you are choosing. Okay, so if you're picking up the largest or smallest element as your pivot, in that case that will be your worst case. Okay, so you will end up using extra memory. Okay, so I will show you how. Okay, so now what happens, let's first talk about partition. So in the partition algorithm, you will see we are passing in the array and the beginning and the end. So you have your beginning index and you have your ending index. Okay, so now let me just have it here. Okay, so now demonstration. Okay, so now you have this thing, right? You have this array in place. Now your partition is called. Okay, so now obviously you will be checking, you will only partition, right? This condition, you will always partition your array in such a way that you're not exceeding or you're not partitioning what has been already partitioned, right? So this condition helps you do that. Okay, that you should not exceed something that has been already partitioned. Okay, and you will see how why this is very important. Okay, so now after that you will partition your array. So now what does partitioning mean? You will pick one element and you partition based on that pivot element. You will partition your arrays. That means you have one pivot element, and on the left hand side you have all the elements that are less than this, and on the right hand side you have all the elements that are greater than this. That's it, that is your partition. So now let's see how partition works. Okay, so you picked up one element, that is the end of the element, right? End of the array. This element you picked up as your index, as your pivot. You also have one index that is known as pivot index. Okay, this is your pivot index, and currently it is at -1. Okay, so now let me pick an example. Okay, so now this is your pivot, right? This is your pivot, this is your end, this is your beginning. Now once you have picked up this element, right, as your pivot, now you have a pivot index over here, which is p index, which will help us to arrange the array in such a way that all the elements on the left hand side, that is the whole objective of this. So you have this pivot, and all the elements that are on the left hand side are less than pivot, and all the elements that are greater than pivot will be on the right hand side. Okay, so you have this pivot index at -1. Done. Now what happens, now you will iterate from beginning to end -1. So from I will be here, and you will iterate from this to end -1. Why end -1? Because our last element is our pivot, and we will not take that because that is the element with which we will compare it. Okay, so that is why end minus 1, so not the last element. Okay, done. Now if ARR of I, if this element is less than pivot, okay, if this element, that is this element, is less than pivot, so obviously it will be on the left hand side. So what we will do, we will increment this pivot index. Now this will be pointing to here, this will be pointing here, pivot index pi. Okay, now once we have incremented it, then we will swap these elements with itself. In this case, both these elements, that is, let's suppose here you have 5 and here you have 10. So 5 will be swapped with itself. Why? I will tell you. In first step, it will not make any sense, but I will move once I will go through this entire iteration, things will make sense. Okay. Now this is done. Now what happens in the next iteration? I will be incremented. Okay. So now let's suppose in this case we have 11 over here. Okay. Now in this case, it is not greater than, it is greater than 10. So nothing will happen. This thing will not be executed. Now I will be incremented. Pivot index is already on this position. Okay. This time around you have 12. Nothing will happen. This time around I is here and you have 6. Now this pivot index, how crucial it is, because it is pointing to that element where it is pointing to that index where all the elements from that index to the left hand side are smaller. Okay, so now you have this 6 over here and you compare it with 10. Now it is less than. So now what you will be doing, you will be swapping it. First you will increment it, so that is why the increment is there. Now you incremented it, pi will be here, and now you will be swapping these two elements. Okay, p index and ARR of I. So now this is 6 and this will be 11. So I'll not consider the rest of the cases. And if you have, let's suppose you have 6 here, or let's suppose you have a 4 here. Now again, your pivot index is at this position, your pivot index will be incremented, and you have your 4 over here, right, and you have your 12 over here. Okay, so now this is this happened, an entire array apart from this element is done, right? Now at the end what happens, we are swapping with the pivot index plus 1. Now this, at the end, this and this element will be swapped. So you have 5, 6, 4, and then this and this element will be swapped, right? This and this element, that is 10 and 11 will be swapped, and you have in between you have 12. So you see this element is the pivot index, and all the elements on the left hand side and all the elements on the right hand side follow our principle. That is, pivot index is the pointer, and in the, when you sort this array, this position will be there for the 10th. Okay, in the entire array, when you sort this array, this position will be fixed. This is its original position. So in every partition that you do, every time your pivot index will have its original position. Okay, done. Now what you will be doing, you will be returning the pivot index plus 1. That means you will be returning this index that is there, which is nothing but 0, 1, 2, 3, 4 and 5, which is 0, 1, 2, 3, 4 and 5. So 3 will be returned. Now what happens to that 3? So now if you go back to here, now this pivot index is 3. Now this will not be considered. Now you will be calling quick sort function again on what? Okay, again on this part, and this will go from beginning, that is from, okay, 1 minute, yeah, that is from beginning, that is 0, to pivot index minus 1, because 10 is already at its original position, which is index 3. So pivot index minus 3, so 0 to 2, again quick sort will be called. And similarly, what happens when this thing entire left part is done, what happens, we'll call this function on the pivot index plus 1, that is 4, to the end of the array, that is 5. So again it will be called once this entire left part is over. Okay, and then you will be calling this on the right hand side. Is this thing clear, guys? Is this pivot and how you partition it? Okay, so if you observe carefully, now you have this pivot index, that is 7. You have this pivot index at its original position. Now you will be calling this on this side. Now this will be your pivot, and this will be your beginning, this will be your end. In this side, this will be your beginning. Obviously now entire left part will be first covered. Okay, so next time around again left will be called. Okay, again you will be doing the partition. Again this 5 and 6 will have its original position. Now this 6 will have its original position. Then you will be remained with 5. Now in that case, beginning and end are not less than. If you observe carefully, I wrote beginning should be always less than end, and then you can call that functions, call those functions, which is not in the case here. Now once this entire left part is done, now you will move on to the right hand side and call it in similar fashion. Now this time around this will be your partition. Once this is done, this will be your partition, because again beginning and end are at the same position, nothing will happen and you will get your sorted array, right? This is the whole demonstration. Now implementation is similar to what we have seen. You have p less than r, and then you call the partition, then you call quick sort on the left hand side, quick sort on the right hand side. And in the implementation you have similar, you pick up the last element, you have pivot index, and then you swap them, and then at the end you will swap them again. Done. And if you talk about time complexity, since you have an outer loop and the inner loop works, in the worst case it will work n square times, because you are picking, either you are picking the largest element or you are picking the smallest element, so that will require multiple swapping. Okay, so every time you need to swap, so every time it enters that loop, inner loop, and every time the swapping will happen. So if that is not the case, in the worst case it will go from n square. If that is not the case, if you randomly pick any element randomly, or you pick the last element or you pick the first element, in that cases it can go through average case or best case. Okay, so partitioning is done in this way. So this is the time complexity. And what about the space complexity? Since you are not using any auxiliary memory, you might be thinking, okay, it will be order of 1 because you're not using, but you are using recursion, and whenever you are using recursion, a call stack or the activation record is formed, and that activation record will contain, in the worst case, all the recursive calls. Okay, that means n recursive calls will be on that activation record. So if you're using that approach which we have seen, the time complexity will be big O of n, because all the elements in the worst case will be there on the call stack. But if you modify it, and will not go into that modification, but you can check after the session is over, you can check, and once that if you modified it a little bit, then you can reduce the number of calls, those elements or function calls that are on the call stack, that can be reduced, and in that case it will be log n. Okay, done. Cool. So just quickly confirm, and if you have not understood, we have already exceeded the time limit, you can always revisit this session and watch it maybe 2-3 times, and just to get the intuition and all those things. Okay, cool guys. So if you have any questions, put it in the chat, else we are going to conclude this session. I hope you enjoyed this session, and always show us some love, like us, like our video, subscribe to our channel, and always share it with your friends, right? So that they will also understand some of the concepts. Okay, cool. So thanks a lot guys. Now I'll be dropping off from this session. If you have any questions, just quickly write in the chat. Thank you guys. Thanks a lot. Harsh, we were planning to go for 5 sorting algorithms, but since it took some time, so that is why 4. Okay, so we have already one more in this session. Yes. So we have already we were planning to go for the merge sort as well, but since that was not possible, so that is why 4 in this session. Okay, Harsh. Okay, thanks a lot guys. I'm concluding this session. Thanks a lot.